Hey everybody, welcome to this talk on edge computing and mobile robotics. My name is Sean Kelly. I'm a software engineer with IFM focused on 3D perception hardware and solutions for mobile robotics. You can find me on Twitter at @TheSeanKelly. IFM is a sensor company that was founded in 1969. Today we have over 7,000 employees and we operate in 93 countries worldwide. Our daughter company, PMD, designs a 3D time-of-flight depth sensing chip, which we embed into industrial 3D cameras. Together, these technologies produce what's known as a point cloud, or a group of 3D points in space with X, Y, and Z information. IFM, as well as our customers, can use this information to produce solutions that help robots perceive and interact with their environments. So you've probably heard the term edge computing before in the context of cloud computing and IoT. The idea is that by offloading work from your central data center onto edge devices, whether they're cell phones or smart connected sensors, you can enhance the user experience of your application by reducing latency, increasing responsiveness, and it also reduces the workload on your data center itself. Another way to think about this is a transition from a centralized computing model to a decentralized computing model. In a centralized world, there's a single entity referred to as a node, which is responsible for computing all of the work in the system. This is the basis of the mainframe model in the earliest days of computing. There'd be a single system which did all of the work. In the mainframe model, the idea of a distributed node did exist through terminals. These were individual workstations that could remotely access and work with the mainframe. However, these nodes weren't really nodes. They were monitors, keyboards, and modems. And they simply facilitated remote access to the mainframe. All of the work was still happening on the mainframe. All the scheduling was there. None of the work was offloaded to the nodes. In the 80s and beyond, as the compute capabilities of these nodes started to increase with the rise of personal computing, we started to see the client-server architecture. And this is where you'd still have a central server that was responsible for orchestration and shared work, but it would also be able to dispatch work out to various nodes to accomplish individual tasks. This is really the first instance of modern edge computing at work, though it didn't have that name. When we get into a cloud world, this picture pretty much stays the same, but there's a key exception. That central node is no longer a server in your data center. It's a server somewhere in a public or private clouds anywhere in the world. And those nodes, similarly, could be anywhere in the world. So you could have some service running in a Bay Area data center, and you could have users in Asia, Europe, anywhere across the globe. And the key problem here is that when you're dealing with latency and network communication, the users in Europe and Asia are going to have a much worse experience compared to those in North America, assuming you have a North American data center. A concept that's risen in popularity lately in the edge computing world is that of an edge gateway. And these are really, you can think of them as mini servers that exist scattered throughout the world, and their purpose is to act as a cache or a local service to handle geographically devices much more efficiently. So you might have an edge gateway in New York to handle the New England area for all the devices communicating with that gateway. You might have one in the south of the US. You might have one in any distributed, my point is it's at a micro level within countries. It's not even continents. And this serves a couple things. The first is clearly it's a latency win. If the nodes are communicating to something, if you're in Boston and you're talking to a server in New York, that's a much better experience than talking to a server in San Francisco. So it just increases the responsiveness of that node and lets it get its job done quicker. The second is it acts as a cache and or a data reduction mechanism to reduce the communication back to the central. The edge gateway can handle most of the computation and only needs to communicate with the central service when necessary. This is an overall win for system architecture and resource planning. When we start to consider how to apply these concepts from edge computing to robotics, there's a couple different ways to look at it. The first is at a macro level, if we're considering an entire fleet of robots. You might have some centralized fleet management software, which is responsible for a variety of tasks. These could be software update, it could be monitoring the health of the fleet, it could be scheduling individual missions to individual robots. Obviously, you've got a group of distributed robots out in the field, and these robots are each responsible for individual tasks and missions. Now let's say a group of these robots is co-located in a specific facility, in a specific warehouse, trying to move pallets around a facility. These robots need to coordinate at a much more fine-grained level than they need to communicate with the rest of the fleet. And at some point it stops making sense to have a central fleet manager dealing with the nitty-gritty details of local planning for each one of your robots. This is where the concept of an edge gateway starts to become interesting for robotics at a macro level via warehouse planning. You might have a server that's dedicated to control the day-to-day operations of a specific facility and then replicate this out to all your different sites. Furthermore, this warehouse planning system reduces the workload on your fleet management because each robot doesn't need to communicate with your central service to do its job. The warehouse planning system might only reach out to the fleet management service to notify about the state of the fleet or to accept software updates and push them down to the robots. The second way to think about edge technology for robotics is at the micro level, and this is where we're going to spend the remainder of this presentation. Let's consider an individual robot. An individual robot typically has some core central controller running on a high-end CPU or a high-end GPU. It's this controller's job to execute and schedule all the tasks, from the highest general mission, what the robot's core job is, all the way down to what the voltage being applied to the motors to make the wheels spin at the right velocity. The controller facilitates this through various subsystems. One example is the safety subsystem, whose job it is to make sure the robot stops immediately in the presence of any danger, any human, any obstacle. Or it might be the navigation subsystem. It's this subsystem's job to determine where the robot is and how to get it from point A to point B. The motor control subsystem. Once the robot knows where it needs to go and why it needs to go there, you need to actually make the wheels turn. On the other side, there's the whole input problem. In order for a robot to do its job, it needs to know where it is. It needs to reason about the environment. And to do this, robots are made up of a variety of sensors. You can have cameras, 2D or 3D. You can have IMUs, which stands for Inertial Measurement Unit, measures velocity and speed. You might have LiDARs, which are kind of a long-range 3D radar type of information. And together with all these sensors, the robot can understand a little bit more about its environment so that it can act in a sensible way. So there's a lot of ways where you can start applying the idea of computing at the edge to a robot system architecture. The first is by offloading work to dedicated processing. And this is especially true in the context of applications like safety or motor control, where there's a high degree of real-time operations going on. These systems need to operate in real time, reliably, 100% every single time. These are jobs for microcontrollers. And so it's a great idea to think about adding extra microcontrollers to handle these tasks in a dedicated way. And this is really a form of edge computing. You're pushing compute off of your central controller onto a distributed node, even though it's on the same physical device, the same robot. It's a distributed node in the compute graph. And by doing this, you offload a lot of the complexity from the controller to these individual microcontrollers. And they do the job very well. They do it in a way that the larger CPU with its dynamic scheduling, it just couldn't achieve real-time performance in that way. Another trend we're seeing is the rise of smart sensors. So one of the key elements of any perception algorithm is data filtering. You have raw data coming in, you need to reason about it, but before you do that, you've got to deal with noise. You've got to deal with artifacts. You have to merge things together and process the data before you even get to work on the core algorithm. Well, a lot of sensors are starting to add computational resources to the sensor themselves rather than offloading these tasks to the controller. However, that really just scratches at the surface of the problem. I mean, if you look at all the sensors on the right-hand side, you could have many different cameras, IMUs, LiDARs, various types of sensors. Together, these are producing a tremendous amount of data. And this tremendous amount of data could easily exhaust the resources available to the central controller and even to the network. Let's say these are all Ethernet connected devices. You could easily flood a gigabit network with just camera frames. And this is a great application of the edge gateway. And here I'll call it the perception system. So this is what we'll be talking about. It's the idea that having some dedicated system on the edge of your robot, so a dedicated piece of hardware processing that isn't part of the core controller, to handle these perception processing tasks can actually enhance the overall system architecture and design of your robot. Here's a typical robot. This is an autonomous floor scrubbing robot by one of our partners, Brain Corporation. And you can see it's got a lot of sensors on it. Processing this sensor data at the edge through a perception subsystem, which again is that idea of an edge gateway that's local on the vehicle, you can start to enhance the overall system design of your robot. For one, it makes it easy to add specialized compute nodes into your compute graph. Things like GPUs are becoming increasingly popular for AI, machine learning, and computer vision workflows. Rather than upgrading your entire central controller to have some GPU resources, you can simply add an edge node that has a GPU on it. Another topic is that these sensors often communicate over low-level, board-level interfaces like SPI, I2C, or MIPI CSI. Higher-level CPUs don't always expose these buses, and you'd need, in a centralized model, you would need to convert that data to something like Ethernet or USB. That conversion is unnecessary, and it simply adds latency and extra compute time. Instead, by computing this information and processing this information at the edge, you can consume the data directly off the board level interface. Sensor fusion is the whole idea of bringing multiple sensing modalities together to solve a common problem. Every type of sensor has its strengths and its weaknesses. And by fusing the data together, you can maximize the strengths and minimize the weaknesses. Doing this at the edge has advantages because all the data is in one place to begin with. It comes straight off the sensor onto the centralized or the decentralized perception subsystem, and it's handled right there. You don't need to worry about shuttling it all around the different nodes of the device. Time synchronization. This is really a subpoint to sensor fusion, but the idea here is that these vehicles are in motion, and their sensors are not necessarily capturing their data at the exact moment. So it's important to be able to correlate time and figure out exactly where the robot was when a given sensor recorded its data. Again, doing this at the edge has advantages. It's often a lot easier to synchronize time in hardware. You have much more fine-grained control over how time is recorded through, say, GPIO timer snap registers or things like this. And again, having one dedicated system handling sensor input, you've got a single clock to worry about. You don't need to worry about synchronizing the tick counts between all your different sensors and how they relate to your central controller. It's all handled at the edge. And finally, data reduction. By consuming all of the sensor data in one distributed node that's, it's not the central processor, it's off-board that, you reduce the workload on the central processor because the perception subsystem handles the task of fusing the data, merging it together, reducing it down to something actionable, and then it only needs to interface with the central controller when absolutely necessary and when it has actionable information to work with. So if you're on board with this idea and you're ready to get started developing your software and developing your robot with some of these edge ideas in mind, there's a lot of technology out there that'll help you start. This isn't going to be an exhaustive list, and nor is it an in-depth tutorial, but just to give you some ideas of where to start. The first is the idea of distributed computing. Distributed computing goes hand in hand with decentralized computing. The idea with distributed computing is to compartmentalize your software into individual modules that are as standalone as possible. And this promotes testing, it promotes iterations, iterability, like you can iterate faster. And it also promotes flexibility for system design. If you have your software system designed in a distributed way, it becomes very easy to move components around. Say you had a centralized system today and it was a distributed computing model. It'd be very easy to take one of those nodes and push them off to some edge device to do the work there. I have the ROS logo here. ROS is the Robot Operating System. And this is an open source system that's really a distributed computing middleware. It facilitates the computing model to make this stuff happen, and it also facilitates a standardized communication model so that all these nodes are interoperable with one another. Using something like ROS just makes it easy for components to work together and to move around. The second idea is that of application containers. This is the notion of packaging your core application along with all of its dependencies and everything it needs to do to get the job done. Again, this is not a new technology, but there's various implementations like Snapcraft, which is a canonical solution, that's designed specifically for the IoT world and translates very nicely to robotics. Again, it builds on the same idea as distributed computing, where it makes it easy to move components around and to actually deploy to the edge on your vehicle. And finally, there's a lot of edge-first devices on the market these days. The most obvious example is NVIDIA with their Jetson line of GPUs. The Jetson Xavier is the top of the line, and it kind of bills itself as a replacement for your central compute with a massive GPU, massive CPU resources, the all-in-one solution. However, they also have the Jetson Nano, which is about $100. It's similar to a Raspberry Pi in form factor. And they have a TX1 and a TX2. These lower-end devices are great candidates for perception subsystems. So you wanted to have just a standard CPU as your controller and do a little bit of GPU work on your perception side, that's a great way to go. So now we'll look at a couple case studies of how this is applied in the real world. This is the Microsoft Hololens. It is an augmented reality headset which uses sensors to perceive the world and see through screens to render 3D content and project it onto the physical world. It's a self-contained device that is worn on the user's head. Now this isn't a robot, obviously, but the perception side of AR/VR is actually nearly identical to that of robotics. You need to have a variety of sensors that are outputting raw data, and some CPU needs to make sense of this. In this case, the CPU needs to be extremely low power because of the thermal constraints, the power constraints of this being an all-in-one headset. However, at the same time, it needs to be extremely responsive because in an AR/VR situation, it only takes about 10 milliseconds of latency to induce motion sickness or just create a poor experience. And so you can clearly see the problem. There's no way to have a low power CPU, a low performance CPU, and also a high responsive, high performance CPU. So the concept of an edge gateway is applied here. Microsoft developed a custom piece of silicon called the HPU, which stands for Holographic Processing Unit, to serve as kind of an edge gateway within this self-contained device. And it hits on all the topics we just spoke about. It's a specialized piece of compute. It does very specific things in hardware, optimizing for thermals and power. It handles the low-level sensor interfaces for all these cameras. It fuses all the data together. It synchronizes the clocks between all these cameras very efficiently and very accurately. And it reduces the data. Instead of raw sensor data coming across that communication layer, you get information about the pose, the hands, the positions of the user's hands and surfaces. It's actionable, small pieces of information. The next example is the IFM palette detection system. This is an algorithm that uses the O3D 303 camera to determine the position and orientation of pallets and racking systems with respect to an AGV. The solution is implemented as an edge solution. We have the IFM O3D 303 camera, which is the actual device responsible for imaging the scene, which has compute capabilities on it. The palette detection system algorithm itself runs embedded on the device and simply communicates to the outside world through a lightweight TCP/IP protocol or a CAN bus protocol, if that's what the vehicle happens to use. This is exactly what we're talking about with edge compute. Instead of outputting the 500 kilobyte point cloud to a host controller and asking it to crunch the data, we're producing actionable outputs. We're only transmitting the information that the vehicle needs to do its job. There's a secondary benefit that I haven't quite touched on, but it becomes apparent when you're considering third-party solutions like this, and that is the simple integration. As an AGV manufacturer consuming a third-party component, it's a much more attractive scenario to simply have to mount a camera, apply power, and implement a wire protocol, as opposed to installing and maintaining IFM software on your host controller. You don't need to worry about the workload that PDS adds to the system. You don't need to worry about the cycle times. You don't need to worry about the resources that it consumes. It's all self-contained on that device. Now we'll have a short hands-on demonstration showing how you can use edge computing concepts to enhance vision workloads. For this demo, I'm going to use the IFM O3D 303 time-of-flight camera. It uses IR light to illuminate a scene and measure the depth information, and it transmits that information over a TCP/IP protocol. We'll look at two separate programs, and I'm going to run them locally on my laptop, which has an Intel i7 processor. I want you to think about that laptop as if it were the central controller on a robot. We'll also take a look at running the same two examples embedded on the O3D303 as an edge solution, and we'll talk about some of the advantages in doing so. The two programs I'm going to show you are written for ROS, which again is just a great system for distributed computing, especially for robotic applications. And if you want to learn the details about that, you can visit ros.org. And finally, all the source code that I'll be using is here on my GitHub. All right, so this won't be an exhaustive ROS tutorial, but there's a couple concepts that you need to know. The first is that of a node. For the purposes of this demo, simply think of a node as a program. It's an executable, it has an entry point via a main function, and it does a task. The other key idea is that of a topic. A topic is one of several communication mechanisms available in ROS, and you can think of it as a named pipe that has a type associated with it. And so here you see a list of topics with names. So clicked point here is a name of a topic, and that topic has this type, which is a well-defined message format within the ROS system. So let's look at a node. So right off the bat, if we go down to the main function, here's the entry point to the node, which is again simply a program. There's some boilerplate to initialize the ROS subsystem. We add a couple of node implementations. So these are classes. The first one is called the IFM 3D ROS2 node. This is our standard driver for interfacing with our cameras in ROS. So I'm going to use that to source point clouds. And then I wrote this separate compute max depth node, which I hope you can guess what it does. We add both of these nodes to the ROS subsystem, do some work to start up the camera, and we spin forever. So here's the implementation of that compute max depth node. It's a few things going on. The first step is we create a publisher. And again, a publisher in ROS, for a topic in ROS, you can have a publisher or a subscriber. A publisher is an entity that adds new information to a topic, and a subscriber is an entity that registers to be notified when data is available on the topic. So we'll see an example of both of these. Here we're creating a publisher. We give it a name, we call it max depth, and we assign it a type, a float 64. Similarly, we create a subscription. We want to subscribe to this topic, which comes from that IFM 3D driver. It's camera cloud, and we know its type, point cloud 2. We're essentially registering to be notified anytime a point cloud is available from the camera. In the callback, this is where we handle the message. What we do is we convert the message from a ROS message into a PCL message. PCL stands for Point Cloud Library, and it's an open source system that's very common for 3D processing. So we simply convert the message here. Then we use a Point Cloud Library API to compute the maximum and minimum points within that cloud. We'll log some information to the screen so we can see what's going on. In this case, we're going to print the height and width of the cloud, which is the imager array dimensions. And we're going to spit out the maximum X value in the cloud. X is the vector that goes straight out away from the camera, and you can think of it as the depth value. And finally, what we're going to do is take that max X value and we're going to publish it on that topic we created earlier. So this is essentially a node that's consuming entire point clouds and emitting the maximum X value, a single floating point digit. So let's run it. And we can see there it is running. That's our logging statement that we have over there on line 58. And if I go over here and stick my hand in front of the camera, you can see it's a live demo. So a couple things to think about. First, just to illustrate what I was talking about earlier, if we list the nodes again, you can see a couple new nodes have popped up. /camera is the IFM 3D node that's driving the camera. And this is the node we created and looked at in the example. Similarly, if we look at topics, there's many more of them, and the one that matters here is this max depth. This is the topic that we just created, and we assigned it a type float64. So if we go ahead and subscribe to that topic here in the terminal, you can see the data coming across on the topic matches what we're outputting. This makes sense. Now again, this is running locally on my i7. We're taking the entire point cloud off the camera over Ethernet onto the device, computing the maximum, and emitting that on the topic. So if we look at Wireshark, which is a network analyzer, pick the network interface the camera is assigned to, and look at utilization, you can see it's quite high. We're actually in the neighborhood of 1,000 packets per second just to output a floating point value. That's not terribly high, but doing this with many sensors, you could quickly overwhelm a network card. So a great way to solve this is through edge computing. I'm going to stop this node. If I SSH into the camera itself, and I'm going to run the same program, which I cross-compiled and deployed earlier. So you can see it's doing its thing. Something interesting to note is I didn't have to restart the subscriber at all. This echo command down here, it simply knows, because topics are unique based on their name and their data type. So that's one of the great benefits of something like ROS, is it makes it very easy to move nodes around and things just happen to work out. So again, we're getting the exact same information we wanted out of the camera, but if we look at our network utilization, it's substantially lower than it was. And this makes sense. You don't need to use all that data just to get a floating point value. So that's an example of doing data reduction at the edge. The next example is going to look at pre-processing data. So I'm going to start the example first, and we can go look at something. So this is RViz, which is a visualizer in ROS. It helps us look at raw data. Oops. And so this is what a point cloud looks like. This is raw data coming off the sensor. Each dot that's colored here represents a point in space that the camera measured. So you can see you can get pretty rich, dense information. Let's say we wanted to reason about this chair in front of us. Couple things I would start with off the bat. The first is the idea that there's all this, so this is a top-down view now. All this information up here is way in the background of my room. And let's say I know that my chair is going to be in the near field. I don't want to waste cycles processing all that information, so I want to drop information that's beyond a certain point. The other thing is that it's kind of a noisy signal. If you look at it straight on here, there's this line right here. It's flying off the edge of the chair. There's a lot of strange dots floating in space, and this is pretty typical for a lot of different 3D sensing technologies. So pre-processing and filtering is almost essential for these sorts of applications. Let's have a look at that. So the code here, it's another node. It's going to look almost identical to what we just looked at, so I'll point out the key differences. We're again creating a publisher, except this time we're calling it filtered cloud, and the type is a point cloud 2. So instead of outputting a single floating point value, we're outputting an entire filtered point cloud. This is the same subscription we looked at on the last example. And in the body of the callback, we're again converting to a point cloud, a PCL message, outputting some information about it. And then here's our filtering. So the first step is I'm going to use a point cloud filter from the PCL library to chop out anything beyond 3 meters in X. The next thing I'll do is I'll use a statistical method called statistical outlier removal, which looks at individual pixels and their nearest neighbors to determine whether or not they're outliers. So I'll apply this filter to our cloud now, and the output is cloud filtered right here. And then finally, I'm going to convert that back to a ROS message and publish it on the topic we created. So again, if we go over here and look at our topics, here is the topic we created, filtered cloud, and the type is point cloud 2. And that's in fact what is being rendered in RViz if we go over here. So again, this is the raw cloud. There's all that stuff in the background. There's the flying pixels on all the edges. If we switch over to a filtered cloud, now this is a lot nicer. We can start to reason about this information a lot better. The downside is we're actually doing a tremendous amount of work. So if I filter to pre-processed, so right here at the top, this is, if I scroll over, you'll see it, but I checked earlier. This is the process that we're running in our ROS node, and we're consuming almost half an entire core on an Intel i7 just to get to a point where we're ready to do some work. That's not really a great use of resources, but it's necessary. This is a great candidate to do on the edge because it's the sort of thing, it's going to happen exactly the same on every single frame before we can do any work. So by pushing that sort of task off to the camera, so again, I'm going to run the same node cross-compiled and deployed to the camera. And we can go look at our visualizer and see that indeed we're getting data out of the camera. So it's the exact same thing happening, except we're not utilizing very many resources at all to do it. In fact, there's no process running on the host controller. There's no drivers, there's nothing. We're just getting the data over the topic. So those are a couple examples of hands-on how we can use the idea of edge processing to enhance some workloads that we find in computer vision. Edge computing is a term common to cloud and IoT, but its ideas are increasingly being applied to robotics. It helps enhance system architecture by managing workloads and introducing specialized compute devices. It improves perception pipelines through data reduction, pre-processing, and sensor fusion. And it increases overall agility by promoting modular designs with easy integrations. Thanks for listening, and if you have any questions, stick around after this talk, or find me on Twitter at @TheSeanKelly. All right, so let's get some questions going. So we have, let's see. You refer to the perception system as an edge gateway. Doesn't this imply some cloud connectivity, and is raw data being pushed to the cloud? So no, in this case, what I was referring to is the idea that I was using the edge gateway idea as an analogy. So in this case, the perception system is functioning as an edge gateway where the robot controller is functioning as the server. So again, it's all contained within that device, but the processing, the vision processing system is actually acting like a gateway by doing some data reduction, doing some pre-processing, and minimizing the workload on the server, the core controller on the robot. We have, so this user liked the ROS demo and wonders if we can write ROS modules in Python. Yep, ROS supports a bunch of languages, mostly C++ and Python. You can learn more about that on the ROS website. I suggest that's probably the best place to go for that question. We have, let's see here. With decreasing costs for high-powered GPUs, like the Jetson Xavier, so again, that's NVIDIA's top-of-the-line, very large GPU and CPU. What are the reasons to prefer a separate perception system from something like that? That's a good question. I mean, if you're building a vehicle from scratch that does have something like an Xavier in it, it starts to look like, well, maybe that system can handle everything. And it very much comes down to a question of your system architecture and your system needs. In general, I think the modularity has a lot of benefits. So again, some of the things that I spoke about specific to that question are just the ability to have a modular system, particularly when it comes to third-party components. You might not actually own the design of your entire system. You might be pulling various systems from other vendors, and it's a great way to pull stuff together in a distributed way. And then another big one that I run into a lot is the hardware interface topic. So sure, you might have a large GPU that can do a lot of processing, and you'll have a lot of cameras that you want to integrate. But if it's something like a MIPI CSI interface, which is a board level camera data bus, now you have to design a carrier board to handle that input and convert it into your thing. And that can become a very expensive, almost a monolithic hardware design, to build an entire carrier board around a single thing. And in many cases, especially if it's a one-off sensor here and there, it could become a cheaper or just more sustainable solution to design a one-off board to push to the edge of the robot and do all the processing there and convert it back to something like Ethernet. And then even with Ethernet, there's always latency concerns. So depending on how large your data set is of your sensor that you're trying to integrate, it becomes, there's a little bit of a latency hit to transfer it over Ethernet versus processing it, doing like a median filter, or the filtering example I showed with depth and doing that on the edge. You don't have to worry about the latency of transferring it over Ethernet. So I hope that clears that one up. What do you think about edge computing and 5G? So honestly, I am not a cloud IoT person. So I can't refer you to any authoritative information on 5G. I do know there's a bunch of people hanging out in the Telegram from Canonical as well as other community members. So maybe they'll be able to answer that question, but just opinions about 5G and edge computing. Or you can reach out to me on Twitter, and IFM has a group of, we do a lot of cloud infrastructure for warehouse automation, so I could point you in the direction of some of our people that are more experts on that topic. Let's see here. Questions are rolling in. What are the minimum hardware requirements required to run a ROS node in a device? Wouldn't that make the device more bulky? Depends. So I was running that demo on an IMX6, which is it's a quad core ARM processor. Well, it's got a dual and a quad. I'm using the quad core in our camera. It starts to push the limits for vision. It's not so much about ROS; it's about the workloads of vision. You're pushing the limits of that. But that's a chip from 2015. So if you're looking at modern things like Jetson, like the TX2, for example, or even the Nano, it's not a whole lot of overhead to add ROS. And then you take it a step further, there's actually projects that are doing what's called the Micro ROS project, which is a stripped down version of the ROS communications layer that runs embedded on things like M0s, M3s, very, very low level processors. So there's some options out there. Again, I would look at the ROS website and search for Micro ROS for that one. What do you prefer for edge computing, NVIDIA Nano or Raspberry Pi? Totally depends what you're trying to do. I think, the NVIDIA Nano is a vision system, vision/AI. So if you're doing any of those workloads, that's absolutely the way to go. Raspberry Pi is just a cheap all around. And again, it depends. What's the purpose for this? If you're talking industrial applications, I don't think either of these things on their own are going to cut it. They need to be wrapped in some sort of industrialized package. That's a hard one to answer without context of what exactly the application is, if that makes sense. Let's see. How much processing power in the sensor end is needed for an application like the demo? Implying point cloud pre-processing at a reliable frame rate for a mobile robot is a GPU recommended. Again, so I touched on this a little bit, and again, it's context matters here. It depends exactly what the workload of the solution you're doing. There's lots of things you could be doing with 3D data, obviously. Like I said, we have a lot of experience running embedded on our O3D 303, and it does start to push the limits. I'll take an example, the pallet detection system that I mentioned. That runs, so again, the application, let me give you the numbers first. So a single detection of a pallet, if I'm running on my i7 laptop, takes a couple hundred milliseconds. If I'm running it embedded on the camera, it can be around a second. So that's a pretty substantial hit. But the context there is that application is a static application. So these AGVs, these fork trucks, will roll up to their destination, stop, take an image, adjust their forks. This is just how they operate because safety and reliability is important. So in that case, cycle time doesn't matter at all for that application. Quite to the contrary, it's much more interesting to have the whole solution packaged on the piece of hardware so the vendor doesn't need to worry about embedding that solution. So those are kind of two examples of if you're trying to do high streaming, high processing, it takes it takes the compute power that it takes. I don't know how to answer that more specifically, but that's not always the whole picture, is what I'm getting at. I hope that answers that. Let's see, what else do we have? Someone asking about QNX Neutrino, and we use it to manage LGV. I actually don't know what those things are, so I would have to look at that and get back to you. And do I think ROS could be a valid alternative? I don't know those other two technologies. It's hard to say. I do know that ROS, in industry, ROS gets a lot of flack for being stable and reliable. And to an extent, that's true. It did start as it's mostly used in education, right? It started as a targeting education and research and things like this, so it's designed from that mindset. The ROS 2 effort, which is all the demos I showed you were in ROS 2, actually not ROS. That's almost a complete rewrite of ROS from the ground up, and it's built on industry accepted communication layers and things like this. And ROS 2 is it's been a development for a while, and it's still going, but it's definitely to the point where it's viable and it's stable and absolutely worth looking at. Let's see. I think that's all the questions. If anyone has anything else, otherwise, all right. Well, cool. Thanks everyone for tuning in. I'm glad I had a chance to speak to you, and I feel free to reach out on Twitter or in the Telegram chat that's linked below afterwards, and I can answer any other questions. Thanks.